All right, class, in this lesson we're going to take a look at conditional probability and intersections. So conditional probability is having to do with when you're given a situation, and you'll notice this bar right here, F, it's probability of F, and then the bar means given E. It says right here the probability of F given that E has actually occurred. So the general rule is this formula here, and so you're looking for the intersection of E and F divided by the probability of E alone, which is, it all is important about the order that these actually come in. So here we have the F is first, so it's E and F, and then just E, the second, whatever's the second one, it goes down on the bottom. So the intersection of the two on top, and then the second letter goes on the bottom, based on how the formula goes. So let's say, and we're not actually using the formula right here, but let's say we roll a dice and the total showing is greater than 9. What's the probability that the total is odd? To look at that, we'll look at our whole sample space of rolling the dice. So if we have our dice being rolled here, so again here this is 1, 2, 3, 4, 5, 6, and down here it's 1, 2, 3, 4, 5, 6. These are the things that show up on the dice when you roll them. What's the probability that the total is odd, but it's given the total is greater than 9? So it says assume. That's a given. In other words, this is what happened. We rolled something greater than 9. So what's the probability that the total is odd? Well, what that means is we've got to limit our sample space to be not all 36 options, because greater than 9 means that 8s don't work. 9s don't work, in fact. In other words, all of these outcomes right here, that's 9, these are all 9, and smaller, aren't important to the situation. Basically, this is all that's left right here. So the question is, how many of them have a total that's odd? Well, 6 and 4 gives you 10. 5 and 5 gives you 10. 4 and 6 gives you 10. Well, those aren't odd. These are odd right here because these add up to 11. So these ones are good. These ones win. Then this one is even. So out of those, or it's not out of the 36, it's out of just these, which is 6 different options. You see them 1, 2, 3, 4, 5, 6 different options. So out of the 6, there's only 2 that are actually odd. So this is odd out of the 6. So this is the total given, okay? And so then that reduces to 1/3. So in other words, a 33% chance of getting them odd out of greater than 9, okay? So if we were to use our formula, the 2 is representative of the intersection of being both greater than, so this is greater than 9, so we'll say greater than 9 and odd over the probability of being just greater than 9. Okay, so this is, if I had it, so it would be probability of odd given that it's greater than 9, if you look at it that way. So using the notation from the last slide, if you want to look at it that way. Here we go. So you've got, for your literature final, you've got 10 questions assigned reading cards, and you're randomly selected 2 cards to write an essay on them. If you've read 8 of the 10 readings, what is the probability of you getting 2 questions that you can actually answer? And assuming here that you haven't done the reading, so then you won't be able to answer the question on the reading. In other words, we just wouldn't be able to answer this question because you might get lucky, of course, and you know the answer, but you didn't do the reading. So we're saying basically I can do it if there's 8 of them, but then there's 2 that I can't. So what's the chance of me actually getting 2 that I can actually answer? So here we're wanting to computing the probability of the intersection of the events. And so if E and F are the 2 events, then we can use this intersection. So what's the intersection here? And so that's the probability. It's basically using the formula that we just had a moment ago, which is the probability of F given E, and then you just multiply the probability of the bottom to both sides, and that'll give you the intersection of them happening. So what I mean by that is our last formula had probability of F given E equals probability of E intersection of F over probability of E. And if I take this E and multiply it to the other side here, and do it here also, I'll be looking at what is written here. Okay? So in other words, the reason why this is useful is because we can think about this situation as the probability of two different things, the intersection of two events, A and B. If A is you can answer the first question, and B is you can answer the second question. So it's taking this whole situation and breaking it down to this. You want to be able to answer the first question, and you want to be able to answer the second question. So how do we work it out from there? Well, we want to know what's the chances of me doing, again, this is intersection, which means and. Basically, what's the chances of me answering the first question and the second question? Well, that's equal to the probability of A times the probability of B, given that I can answer the first one already. So that's what I'm looking for to answer this actual question. Okay. So here, because I have read 8 of the readings from the 10 that were assigned, we can see that our first probability that we can answer the first question is 8 out of 10. Okay, this probability is 8 out of 10. To find probability of B given A, we have to think about it in words. The probability that you can answer the second question given that you have answered the first question. Okay, that's really what we're looking for. And to do that, the chances of that happening are based on what just happened. So in other words, I have the 8 out of 10, so we're saying, all right, this happened. Given that worked, I got that one. So in other words, I have the 8 out of 10. Okay, so now what's the chances of me answering the next question? Well, now there's not 10 questions I have anymore. There's only 9 questions I have because I just answered one. And there's not 8 that I know anymore because I already got that one. There's only 7 left over that I know that I can actually still answer. So that's where this 7 out of 9 is coming from. Okay, so here it is. Probability of A happening is 8 out of 10. The probability of the next one happening, given the first one already happened, is 7 out of 9. And then if I multiply that together, that is my overall chance of winning on this test and answering the questions correctly. So if I multiply that out, I get 56 on top, 90 on bottom, which is about 0.62 or 62% chance, which isn't, not very good for a test, but 62% chance that I'll be able to answer both the questions on that test. So here we go. We've got a carnival game. Evan will draw 3 colored balls consecutively without replacement from the urn to determine his prize. If he draws 3 red balls, he can choose one of the most desirable prizes. What is the probability that he will draw a red ball, and a green ball in that specific order? So to do this, we have to break them down one at a time. And you can set it up using the formula, but it's a little bit easier just to logically think through this and work it out, where I've got to count up how many total balls are there in this thing. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different balls. All right, so 15 balls. How many are red? 3. So the chance of me getting a red ball the first time I grab is 3 out of 15. Well, the next time I grab, there's not 15 balls anymore because I already took one out. There's only 14 left. There's not 3 red balls now because I already took one out. And there's only 2 left. The last one says, all right, well, what about a green ball in that order? Well, now here, 14 is now a 13 because there's only 13 balls left in there. And how many green are there? 1, 2, 3, 4, 5, 6, 7 different green ones. So the odds of me doing this, or not me, Evan, 3 out of 15 times 2 out of 14, and then times 7 out of 13. So if I just multiply this out, 3 times 2 times 7, 3 times 2 times 7, gives me 42 out of 15 times 14 times 13. So that's out of 2,730. So 42 out of 2,730. If I divide that, gives me a 0.01538, which is about 1.5%. Oops, sorry, 1.5% chance of actually happening. Okay. Here we go. Independent versus dependent versus independent. The last situation was a dependent situation because as I took a ball out, the next one depended on the fact that I just took one out, and the top also depends on the fact that I took a red ball out versus a green ball. So this is dependent. We also have independent events. Independent happens if the probability of F given E is equal to the probability of F. In other words, if I do something to the situation, it doesn't actually affect the probability of the next thing happening. So assume we roll a red and green die. The event F, 5 shows on the red die, and G, the total showing on the dice is greater than 10. Are these two statements independent or dependent? And so what you're looking at is this sample space here of all the different ways to roll the dice. So here, if 5 shows on the red die, would be these right here. Oh, sorry, 5 showing on the red die, I apologize. Just the red die. So let's call this the red one, and this one the green one. Doesn't matter, but call these ones all the red. Well, here's the 5 showing up on all the red die. Okay? And then, so there's that one, and then it says, so basically what's the odds of this happening? 5 showing up on the red die, there's 1, 2, 3, 4, 5, 6 different ways for that to happen out of the 36 different ways to roll the die. And then the next one says the total showing on the dice is greater than 10. Okay, well, total showing greater than 10, that's only 11s and 12. There's only 3 ways for that to happen out of 36, so 3 out of 36. Okay, so our question is then, what's the intersection? Because what we need to do is figure out, to do the formula for probability of F given E to see if it's equal to probability of F. Okay, well, probability of F is 3 out of 36, which is this 1 over 12. Actually, I guess we're calling that G here. Let's see. Oh, no, 3 out of 36. I had it right now, sorry. So this is the 3 out of 36 here. And then F is the, what I just found, which is the 6 out of 36. And our job is to figure out then what's the intersection of them. Get a different color to show up. That'd be wonderful. So all we have to do is take our formula and figure out the given. So the given would be probability of G intersection of F divided by the probability of F. And here, the intersection is there's 1. This one right here. That's 1 out of all the different options. There's only one of them that's overlapping between the two sets. So that's, and this is it. So there's 1 out of the probability of F is these right here, which is the 1, 2, 3, 4, 5, 6, which is covered up, sorry. 6 different ways out of 36. So there's 1 out of 6, or out of 36. Sorry. So this was our 6 out of 36. I think I have this written, so it's a little bit closer. Yeah, there we go. So 1 out of 36. Sorry, I forgot that part. That's where I was screwed up. All right, so here you can actually see it a little bit more closely what I was just trying to write up. The probability of the intersection is 1 out of 36. So that was the 5/6 there. And then the probability of F, which we worked out earlier, which is 6 out of 36. So what we're supposed to do is, using our formula to find a given, so we take the intersection, the overlap, and divide it by the original one, the second part here. And that gives us, if we divide, you can divide in your calculator or whatever, and it'll reduce to be 1/6. The actual math on that is 1 out of 36 divided by 6 over 36. To divide a fraction by another fraction, you flip and multiply the second one by its reciprocal. So the bottom, the denominator, you flip it up and get 36 over 6. And these cancel, and you reduce it to be 1 over 6. That's where that came from there. So in other words, we got the 1/6. The 1/6 is this part. The other part was 1/12. These are not equal, so they are dependent situations, not independent situations. And that's it for this particular section. If you have any problem-specific questions, please let me know through the Ask My Instructor feature of the lab.